Hi, biologists. We're going to go over chapter 3, which is the organic molecules. And this is just going to be part 1 of this chapter. So a couple of vocabulary terms to get out of the way. Organic chemistry is going to be about talking about the branch of chemistry that deals with carbon-containing compounds. Back in the 19th century, chemists discovered that, all of the compounds that contain carbon were from living things. So that's kind of where that word organic comes from. And then the organic molecules then are going to be the molecules that contain carbon and hydrogen. And typically they're going to contain quite a bit of hydrogen atoms. They're going to be called hydrocarbon molecules, but they will at least have one hydrogen atom in them. So let's talk about the carbon atom itself, since this whole branch of chemistry deals with carbon. Carbon has 6 electrons. It has an atomic number of 6. 2 are going to be in that first shell, as you can see here, and it will give us 4 valence electrons. So what that means is, remember that valence electrons like to be paired, so that they have a total of 8 in their outer shell. And so what's going to happen is this carbon is going to want to bond with 4 other atoms, which is going to give us then 4 covalent bonds. And the most frequent partners are going to be hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And if you remember back to chapter 1, we had this little word that we remembered, schnapps or schnopes, however you want to say it, but these are going to be the essential elements for life. And so as you can see from this, that carbon is a huge player in all of the molecules required for life. So it's going to then be the basis for those partnerships with the other atoms. The carbon bond is very stable, and that's kind of what gives it the name the carbon backbone. We're going to talk more about that in a little bit. So carbon is super diverse. It can do lots of things, and it can form really long molecules, as you can see from this picture here. I'm not sure if this picture is in the way. I'm going to make myself smaller here. So it can form super long molecules, and in fact, it can form molecules that we call macro, which is big, macromolecules. And the 4 classes of macromolecules that we will discuss, especially in this chapter, are going to be carbohydrates, lipids, proteins, and nucleic acids. And I'm sure you've heard a lot about, especially the top 3, just within health, talking about, people say they count their macros. These are going to be some very essential elements that we will get through our food. And so we'll talk more about this the rest of this chapter. So let me click, there we go. Carbon can do all sorts of crazy things. So it can actually form single bonds, carbon to carbon here, or with another element. It can also form double bonds, and it can also form triple bonds. The other things it can do is, you'll see carbon in all sorts of different shapes. It can form these branches here. It can form, sorry, those aren't branches. This can form a chain. Down here, it's hiding on mine, but it can form branches, and it can also form rings. The other thing carbon can do is it can form isomers. So isomers are going to be molecules that have the same molecular formula, but they're going to differ in atom arrangement. And so a key idea that I want you to be aware of is that different structures are going to give it different properties and functions. So structure and function is super important. There's different kind of isomers that we're going to talk about. The structural isomer is just going to be where you're going to see that there's going to be a molecule bonded onto a different carbon atom. The cis-trans isomer will show you that these R groups, we're going to talk more about the R groups in a minute, but the R groups will be on different sides of the carbon chains here. So you can see these R groups are on the same side, as opposed to this isomer, which we call a cis-trans, where it's going to be like on opposite sides of the carbon. And then the other one is going to be called an enantiomer, and that one is going to be mirror images of each other. So if you think about a molecule and you'd put 2 molecules on top of each other, they actually don't match up. So I'm going to play this for you so you can kind of see what I mean.
A chiral object is one that is not superimposable on its mirror image. Your left hand is chiral. It cannot be superimposed on your right hand. Many molecules, including important drugs and natural products, are chiral. This is a ball and stick model of a carbon molecule with 4 different groups attached to the central carbon. For example, the 4 groups could be hydrogen, chlorine, methyl, and carboxylic acid. This molecule is chiral. That is, it is not superimposable on its mirror image. The two forms of a chiral molecule are called enantiomers. Using special rules, one form is labeled R, the other S. Enantiomers have mostly the same physical properties, but they behave differently in chiral environments. Molecules may contain more than one chiral center. For example, tartaric acid, which is found in many fruits and in wines, has two chiral centers.
Okay, so as you heard, the mirror images of each other are called, one is called R, one is called S. And if you would superimpose them on each other, you're never going to get them to exactly match up. So again, different structure, different function. So we're going to talk about more about that. One example of this is going to be thalidomide. And so what happened was back in the 1950s, there were all sorts of women who were pregnant and they were having terrible, terrible morning sickness. And so researchers and scientists created a drug called thalidomide, and what that did was help with morning sickness. So fast forward 9 months, what started happening was all of these babies were born with birth defects. And so what they found was that this was a problem with the enantiomer. And so the good enantiomer was helping with morning sickness, but the bad one was causing birth defects. So I'm going to go ahead and play you this little clip as well.
On October 1st, 1957, a new over-the-counter drug was introduced in West Germany that was supposed to basically cure morning sickness during pregnancy. It was called thalidomide. Thousands of women purchased the drug and were relieved when their morning sickness disappeared. And everything seemed great until later the next year when thousands of infants were born with severe birth defects, like brain damage and deformed limbs. Doctors noticed the surge, but at first they couldn't figure out what was causing it. Then, two doctors, Wiedekind Lenz from Germany and William McBride from Australia, both noticed that the mothers of these babies had all taken that amazing new morning sickness drug. By 1961, Lenz had proven the link between thalidomide and the birth defects, and it was pulled from the shelves. But by then, thousands of infants had been born with those birth defects, and nearly 40% of them had passed away. Rules for drug testing weren't as strict back then, and in this case that cost thousands of lives. Even though they were now aware that thalidomide was a problem, scientists still didn't know why. It turns out the answer lies in its chemistry, or more specifically, its geometry. What researchers didn't know at the time was that there were actually two versions of the thalidomide molecule. Thalidomide, which is made up of 3 connected rings of carbon and nitrogen atoms, plus some oxygen and hydrogen, is what's known as a chiral molecule. Chiral comes from the Greek for hand or claw, and chemists often think of chiral molecules as being right-handed or left-handed. And that's because the different versions of chiral molecules, called enantiomers, are made up of all the same parts but arranged differently, just like your hands. If you try overlaying your right hand on your left, you'll see that no matter which way you turn your hands, you can't make them match up. Even if you make your thumbs line up, one hand is palm up and the other is palm down. In other words, both hands have the same 5 fingers, but they're not identical. And molecules like thalidomide are the same way. A chiral molecule has an atom, typically carbon, with 4 different groups attached to it. That's called the chiral center. A group can be anything from a single atom to a long chain to rings. In some cases, 2 groups can even be connected. These groups are kind of like your fingers. In each enantiomer, the groups are attached to the chiral center in the opposite order, so they're mirror images of each other. In thalidomide, for example, the chiral center is a carbon atom attached to one of the rings. It's bonded to 2 other carbons, a nitrogen and a hydrogen. If you position the version of the molecule that's considered right-handed, called the R enantiomer, so the closest oxygen atom to the chiral center is below it, the hydrogen atom attached to the center will be facing away from you. But if you position the left-handed or S enantiomer the same way, the hydrogen atom will be facing toward you. In other words, the 2 enantiomers are mirror images of each other. And because different receptors and enzymes in your body react with molecules in very specific ways, the fact that enantiomers are mirror images means that they might react to things totally differently. In the case of thalidomide, scientists discovered that the R enantiomer helped with morning sickness, but the S enantiomer caused those severe birth defects. One of the most famous, or maybe infamous, examples of how 2 enantiomers affect the human body is methamphetamine. You'd probably associate that name with the street drug, But the molecule can only really break bad when it's in its R formation. The S enantiomer is commonly sold over the counter as a vasodilator, and you can easily find it in vapor inhalers. But the vapor inhaler you just bought at the pharmacy isn't filled with a dangerous drug, because the S version will never be psychoactive. After researchers discovered that only the S version of thalidomide caused birth defects, they thought about isolating the R enantiomer so they could continue to use it to treat morning sickness. But it turns out that thalidomide's R enantiomer can actually switch to the S version while inside the human body, meaning that even if they'd isolated 100% pure R thalidomide, it still wouldn't be safe for pregnant women. But in 1998, the FDA did approve thalidomide, almost 40 years after rejecting it based on the birth defect problems. This time, though, it was approved for treating complications from Hansen's disease, aka leprosy. And recent research is also leading some scientists to believe that in certain cases, thalidomide could help with a number of debilitating diseases, including some forms of breast cancer. They just make sure not to prescribe it to anyone who's pregnant. Thanks for watching this episode of SciShow, which was brought to you by our patrons on Patreon. If you want to help support the show, you can go to
Okay, so sorry, going back. So as you heard, not only was there the good and bad enantiomer, but what happened is that the good then converted to bad. So they couldn't even just isolate the good one. So a really good example of the enantiomers and how they differ, different structure, different function. Again, thankfully we're able to use it for a different purpose, but it took unfortunately a lot of babies being born with defects in order to figure that out. So again, just another example of change in structure, change in function. These are drugs that you probably are very aware of. The ibuprofen for pain, like Advil, and also albuterol. My son takes this for his asthma. And so again, there's two different enantiomers for it, the S and the R. And if you take the S, that's the one that you're getting for the ibuprofen. The other one is just, it's ineffective. Same thing for albuterol, just the opposite. If you take the R, or the S, sorry, it's ineffective. If you took the R, it is effective. So again, driving home, I'm going to say this a billion times. I'll say it now, I'll say it again and again and again and again the rest of the year. You change the structure, you're going to get a change in function. The key concept in AP biology. I talked before about the carbon-to-carbon molecules, the hydrogens around it. We call that the hydrocarbon chain. So what you're going to have is you're going to have, let's see if I can grab my pen, you're going to have a bunch of carbons bonded to a carbon, bonded to a carbon, for example. It's a little scary, but you're going to end up having bonds around it because remember it's going to form 4 covalent bonds. I'm going to write on my presentation. So all of these are going to be hydrogens. This is really bad drawing, sorry. I think you get the idea. Hydrogen here, we have a hydrogen here. This is probably painful to watch. But what happens then is there is usually a group attached to this carbon skeleton, and we give it the name R. Okay, so it's like the replacement group. So what's going to happen is there'll be a group that's attached to the hydrocarbon chain, the hydrocarbon backbone, or the skeleton of the model. And so what this R group is going to be a specific group of atoms that are going to be bonded to the skeleton. And what this is going to do is this R group is going to give the molecule its behavior. So in and of itself, the hydrocarbon chain is not going to give us much of the behavior, but once you put this R group on it, it's going to completely change what the molecule does. So for example, if we take this ethane molecule and take away this hydrogen here, and we would replace it by this hydroxyl group here, what it's going to do is it's going to change it into ethanol, into an alcohol. When you add an OH group, it's going to change it to an alcohol, and it's going to actually change it from being hydrophobic as ethane to hydrophilic as ethanol. And so this is going to be a huge game changer when it comes time for the cell, because the cell is made up of a lot of water. And so whether or not things can dissolve or pass through the cell membrane, for example, it's going to make a big difference. So let's see now if I can get back to my pointer here. Okay. Oh, now this is not going to be deleted on that. That's kind of silly. All right, so let's go ahead and erase this. And so I have a list here of the main functional groups that we are going to be using. And so I would actually recommend, you don't necessarily have to memorize these, but I think it's a good idea to have these somewhat down. because as you go through different molecules throughout the course, you're going to be able to tell pretty quickly based on the functional group and that R group what behavior that molecule is going to be able to have, especially within the cell. So I would recommend just taking the names of these here and then knowing kind of generally what you could even just say for this one, making sure that you know that there's, an oxygen here and the oxygen here, the carbonyl group, that you're going to be able to be able to identify kind of what the name of it is and then what the group is and then generally kind of what behavior it has. And I have a different chart that I'm going to share with you as well that I think kind of even summarizes it a little bit better, and I just forgot to throw it into this presentation. So I will also add that at the end. And then I would just suggest maybe throwing it into Quizlet or something and just every once in a while kind of going back to it. We're going to do an activity in class that will also kind of drive this home. You'll be able to much easier identify these molecules if you're able to kind of see what the functional group is. So that is the beginning of the chapter 3. We're going to talk more specifically about those macromolecules in the next presentation.